And then I'm going to share screen. I see people popping in, the attendance list. Welcome everyone. We'll get started in just a couple minutes. I usually like to give people just 2 or 3 minutes past the top of the hour to pop into the webinar. Thank you all for joining. And then for everyone who has joined, we are recording and we'll publish the link to the recording if you have friends or colleagues who couldn't join us today. And you will, for those who have been on from the beginning, you will get tired of hearing me say it, but we'll get started in just a minute, letting some people join just a couple minutes after the hour. And hi everyone, and don't forget to post in the chat. Once we get started, we'll also take Q&A through the chat and address questions at the end, but please let us know where you're coming from and welcome. It's nice to see people from all over the world. And it is just 3 minutes after the top of the hour. I'm going to go ahead and get started. I have a short introduction here before we hear from our terrific speaker today. My name is Paula Paul. I'm a distinguished engineer with Grayshore Associates, and I'm also a CloudTrack lead for Women Who Code. We have our CloudTrack fellows on the call as well today, monitoring the chat and helping with Q&A. So welcome everyone. Our talk today is from Amanda Gilbert, who's a systems engineer with Confluent. We'll be hearing about Kafka and event-driven architecture. But first, I'd like to introduce everyone to Women Who Code and our mission of inspiring women to excel in technology careers. It's near and dear to my heart, having been in technology quite a while now. And I do share the vision of Women Who Code, which is a world where women are represented as technical execs, founders, VCs, board members, software engineers, product management, quality, engineering, security, every aspect of the world of technology that drives our day-to-day, and everyone should be welcome to participate at all levels. We do have a code of conduct. We're an inclusive community, and anyone's welcome to the community as long as you share the vision and the mission of Women Who Code. We certainly hope that you never need to make use of this, but if you do experience lapses in activity or behavior towards this code of conduct, we want to hear so that we can address those things, and we'll address them quickly. So thank you again for joining. Special thanks to our sponsor for the CloudTrack, VMware. And then last but not least, please do follow us on social media. Join up. We have a Women Who Code Slack for cloud and other different tracks such as front end, Python. So it's a great community. Please join us. And with that, I am going to turn it over to our amazing speaker, Amanda Gilbert, for dropping some knowledge on Kafka. Amanda?
Thanks, Paula. Thanks. Okay, let me share my screen really quick and we'll get started. Okay. Nice to meet everyone. My name is Amanda Gilbert, and I am a systems engineer at Confluent. Basically, what that means is that I work both pre and post sales with customers as their technical resource as they navigate a journey to using Kafka and event-driven architecture. A lot of times, my customers are also undergoing changes within their organization to things like utilizing cloud technologies, utilizing microservices architecture. So usually, Kafka is just a piece of a greater modernization that's going on at companies. My background is specifically in data, although I've been writing code since I was around 15 years old. I got into data when I graduated college 6 years ago, and I've been in that space ever since. So I worked at Hadoop company, Hortonworks. I've also done some consulting in my past life, and now I've made my way to kind of the sales side of things. So that's my background. Today we're going to be going over Kafka just sort of at a high level and also looping it into event-driven architecture on the whole. So where does Kafka fit in with these event-driven systems, and touching briefly on deployment options for Kafka as well. So starting with event-driven systems or event-driven architecture. So they are asynchronous and they allow decoupled services to process events in a scalable, flexible way and to replay data when needed. So those are the key features of an event-driven architecture, but there are many different ways to lay out your architecture. It came from a shift really from looking at data as a state. So back in the day when we had primarily relational databases and they were looking more at the current state, making decisions based on the current state of data. Things like what is a customer's current email address? What is their balance within their account? How much do we have currently in inventory? Or what is a patient's current temperature? These things are all examples of what your state of data looks like. Whereas an event would look something more like a customer makes a change to their email address. They might spend a specific amount of money at a website or physically. They might have a change in temperature, and this becomes a more unique way of making decisions within a company, because instead of just looking at the current state, like looking at my current bank account balance, I might not be able to do much with that. But if I can see, hey, a customer spent $16 at Target.com, 30 seconds later, they spent $120 at Amazon, and so on and so forth. They made a number of transactions within a short period of time. I, as a bank owner, might be able to flag that as potentially fraudulent, reach out to the customer, and anyone who has worked with a bank recently knows that now they'll send you a text message and say, please confirm that you made this series of payments. That comes from the ability to look at events as unique actionable items instead of just the current state. Okay, so talking a little bit to where the need for Kafka came from. So as we started to make this shift towards more real-time type of data processing, so moving from things like databases, data warehouses, and then applications, and a lot of point-to-point connections, using many different tools that all communicate with applications and databases in different ways. This is really difficult to scale because, as you can imagine, as you add more apps and as you add different data sources or systems, you have more and more point-to-point connections. So the growth of this just becomes almost unmanageable. It also doesn't allow you to process your data in flight. So instead of being able to make decisions as your data is moving across between systems, it has to land in a system or application in order to allow you to have insights into the data itself. It tends to be more batch oriented because of that. So like a lot of customers I talk to, they'll say, we have a process that runs every 60 minutes and then we make decisions based on that. But a lot of times 60 minutes doesn't cut it, right? By the time you're making a decision based on that data, you're already behind, and so your decisions are not really that useful. We have a lot of new technologies coming about that allow us to do really interesting things. So instead of just having standard traditional relational databases, we had like document stores pop up, caching systems, NoSQL databases. And then we also brought about the ability to do different type of big data processing. So things like Hadoop or Apache Spark, these all came in the mix. Because of that, we needed a different way to communicate data between our applications and our data warehouses and databases and different advanced storage systems. And that's where Kafka came about, and that's where it was derived from. And now it's really been built out to be a full streaming platform. So more so than just a publish subscribe messaging system, it allows you to do ETL on the fly, stream processing on the fly, right? All of these things that were built into separate technologies are now being consolidated into a single layer between your applications and your databases. Okay, so going into EDA models a little bit, so that's where the need came from, but what does that actually look like in practice and what does that mean? And I have a lot of people ask me this, right? So how long do I store my data at the data layer in the middle? Do I have to have a different database to store it, or can I store it all within the Kafka layer? And the answer is it totally depends on the use case. So I would say there are four main event-driven models. So event-driven models are event notification, event carried state transfer, event sourcing, and CQRS. So we'll just dive into those. So the first one would be event notification, which is where a system will notify other systems of events that happen. But it's usually just metadata, and it's usually fire and forget. So it's, this thing happened, my customer changed their email address, I'm just gonna put it on the queue. If other systems are concerned with it, then they can consume it, but I really don't care if they do. It doesn't make a difference to me if the downstream systems make changes, if they fire off notifications based on it to the customer. It doesn't matter to me, it doesn't affect me, I don't need to know about it. Also, usually because it's just a metadata transfer, the systems that are receiving the data will oftentimes have to reach out to the underlying system if they do want the full data and to be able to update their systems accordingly. So it's more like, hey, this thing happened, if you care about it, let me know, and I'll get you the data. So that would look something like this. A customer changes their address and there's a service that publishes to the queue that there was an address changed. And it scales out pretty well in that you can, as you add additional systems that might care about that change of address, they can subscribe to the queue and get the notification. So it's really good because it decouples our producers from our consumers, meaning, like I said, it's fire and forget. They don't really care what is done with it. But there's not really a statement of overall behavior, so the systems don't do a really great job of tracking how that data may change. That's not necessarily stored within the middle layer, so that can be kind of problematic. The second option that you have is event carried state transfer. So what this means is, let's say there's a state change to your data. That data is transferred to your other systems through events. So the main difference here is it's not just sending metadata, it's actually sending the data itself so that downstream systems can consume it. This is even greater decoupling because systems are not reliant on each other. So let's say we have an underlying system that sends an event change. Let's say we're tracking CDC changes on an underlying database. That change is sent out and put on the queue, and the data is sent with it. And then our downstream systems can consume from that queue and get the change directly off the database. So it doesn't just need to know that, hey, there was a change made and now I need to reach out to my underlying database. It actually gets the data with it. Because of this, there's lower load on the underlying systems because these consuming systems don't have to reach back out to the underlying database every time that they care about a state change that was made. Yeah, so this would be a visual representation of this. So there is a change and you get not just the change, but also the details of the change. And so the system that's consuming from the queue would also need to maintain its own version of state. So that's why here the insurance quoting system will also have a database of customer information that it will use to track any changes that are made from the customer management system. So as we mentioned, this is great decoupling. it is a reduced load. The only problem here is that, first of all, you're going to have replicated data. So you're now going to have two separate databases that are carrying the same data. So while it does lead to lower latency because you have the data right there when you need it, it also means that eventual consistency is a little bit difficult in this state, because if each system has replications of the same data, but they're not necessarily posting every change that they're making, so they're not necessarily required to. You might have systems that have different store of the data currently and think that the data is in a different state. So you have to deal with that sort of eventual consistency issue. I would say that event sourcing is looked at as like the holy grail of event-driven architecture. And when people think of event-driven architecture, they can sometimes think of it as synonymous with event sourcing, but it's not really synonymous. It is essentially when you will store every single change that's ever been made. It's logged as an event, and then system state can then be rebuilt at any time from the event layer. So as opposed to our last example where each of our systems had their own store of the data, in this case, the middle layer would be the store of the data, meaning that every system would query from the middle event layer anytime that it needed to rebuild its system. Unfortunately, this leads to large amounts of data stored within the middle layer. So as opposed to, if you think about a relational database that has a number of tables, right? Let's say your relational database has a terabyte of data sitting on it. That's just the state data. If you then abstract that out and say, I not only need the state data, but I need every event that's ever happened to get me to this current state stored on the middle layer. And in the case of Kafka, I want it replicated X amount of times, right? That can be a lot of data that you're required to store. So this really only works if you have the right amount of storage for the data. And it also only works if you're able to utilize like cheaper storage systems, or you just have an unlimited amount of money to store your data. So those are the trade-offs there. It's great. It is, like I said, it's sort of like the end goal that everybody has pictured when they think about maintaining an event-driven architecture, because it is so efficient. But it's difficult. It's becoming something that's more possible with cheaper storage and cloud providers rolling out things like tiered storage. It's becoming a more possible vision, but I would say we're still a little bit far away from that dream in most cases. The final option that you have is CQRS. This is, command response. It separates out read and write, and every method is either a command or a query. And Kafka can be used as the middle layer here. Write to Kafka, pull the data out, and then write it to a database to be read. So that would look something like this, right? Your system tells the others what to do with an event itself, or it asks questions of your other systems. Whereas more event-driven systems will have Kafka as a middle layer. They all communicate with each other through that middle layer of Kafka, and they don't necessarily always have like requests for the other systems. They might just be firing it off and storing it in the middle layer and allowing the other systems to figure out what they want to do with the data. Okay, so a brief introduction into Kafka. It was developed at LinkedIn. So the company that I work for, Confluent, is a company that was built specifically for Kafka and for additional IP on top of Kafka, and also support, training, professional services. But Kafka itself was started at LinkedIn. They were able to scale Kafka at LinkedIn to more than a petabyte of data, 4.5 trillion messages per day, 60,000 data streams. And it was the source of all of their data between their different data warehouses, Hadoop structures. So it's highly, highly scalable. It was built specifically for low latency, high throughput, high scalability. There are a few different common architectural patterns that you'll see with Apache Kafka. You froze for a second, sorry about that. So the first one would be, let's say you have a relational database and you want to move it to downstream systems, whether that's a data warehouse or a data lake or an applications level or microservices, whatever the case may be. You might be looking at multiple different streams of data coming from an underlying relational database that you already have that's already set up for some sort of underlying monolithic application. You would use Connect, which is a tool within the Kafka ecosystem to pull data in from that underlying database. And then you would use a stream processing tool, whether that's Kafka stream processing tools itself, which we'll go into in just a minute, or if that's an external stream processing tool, something like Flink or Storm or Spark Streaming or something of that nature. Write the data back onto Kafka and then allow it to be consumed by downstream systems. Within Kafka, you are able to use it many times. So meaning that, let's say you transform your data, you do a join between some sort of application and then your underlying relational database. You make a join at the Kafka layer. You can then send it to multiple different systems. So you can plug in additional consumers as you need and give them access to the data as well. So that's one of the really unique things about Kafka, is that it's not like one solo data pipeline, AKA here's my starting location of my data and here's my ending location of my data and that's it. It doesn't change. It's completely synchronous. Kafka, on the other hand, is asynchronous, and your producers and consumers are decoupled from one another so that you can add additional producers as you see fit. You can add additional consumers, and Kafka will allow you to do that and allow you to scale that way. So the way that that works is that we have writers or producers that produce data to your Kafka cluster sitting on something that we call topics. You can think of that as individual streams of data. Each topic is made up of partitions, and topics are just an immutable log of records, meaning that every change that is made by the producer is appended to the end of the topic or the end of the partition, depending on if you partition your data. And then it is consumed by downstream systems, readers, or consumers. When we think about working with Kafka natively, Kafka is written in Java and Scala, so those are the native clients that work with Kafka. You also can use open source clients, so some of the most popular ones are things like .NET, C and C++, Python, Go, and then there are just a number of open source connectors to Kafka as well. It is unique because it is scalable like a file system, so you are able to continue to scale out what are called brokers. So each node of Kafka is called a Kafka broker, and that is where your data is actually stored. And as you continue to scale out brokers, all that you need to do is rebalance your data across the new broker, and you can continue to scale out Kafka, indefinitely. So it does have high throughput capabilities, high amounts of storage, and because it can be run on commodity hardware, it's highly scalable. But it's sort of like a database in that there is strict ordering. So it is guaranteed that on the partition level within your topic, you will have strict ordering of your data. And it does have persistence. So a lot of times when we think about message queues, a lot of people that worked with traditional message queuing systems will think that the data is stored within the Kafka layer until it's consumed, and then it's erased. That's not the case with Kafka. So it's persisted at the Kafka layer, and you can set the amount of time or the amount of storage that you want to utilize at the Kafka layer. So meaning you could request that it stays on Kafka for a week, and then for that following week, you will be able to replay your data at any time by your downstream systems. So this is what I was just mentioning, right? You do have the ability to reset to a different point in time back to your retention period. So let's say your retention period's a week, then you can replay to a week ago. And as I mentioned, each record that is added is appended to the end of the queue. Kafka is distributed, so there is replication and fault tolerance built into Apache Kafka. There is also partitioning, so that's what I mentioned, how you can partition your topic so that you have the ability to have faster processing times, right? Higher amounts of throughput by having more partitions. And those partitions are spread across multiple brokers within Kafka. So I think I'll get into this on a couple of slides, but essentially it allows you to be more scalable, more fault tolerant, just in case you do have broker downtime. It also allows for elastic scaling. So as you need additional capacity, it is very easy to scale up your Kafka cluster and add additional throughput or storage capacity as is needed. So this is the anatomy of what a Kafka topic looks like. So let's say you have a Kafka topic that has 3 partitions, and those 3 partitions are spread across 3 different brokers. That will allow you to not only have the additional durability of your Kafka cluster, but also to, as I mentioned, increase your throughput capabilities by spreading the load across 3 separate brokers. So over time, as you're producing to Kafka, you will be producing to the end of the log. It is an immutable log of records, meaning that I can't go back to what we call an offset. So each one of these is given in a separate offset that you are producing to. I can't go back in time and reproduce to a previous offset. The only unique difference here is that, let's say you did use something called a compacted topic. Compacted topics only store the current state of the data, meaning that for each key value pair, they'll only keep the most recent change that was made to the data. If that's the case, then each time you append to that topic, it will delete the old key value pair of that specific topic. But typically within Kafka, it's an immutable log of records, meaning that your data will not change. So you will just store each event that's happened. Oops, wrong way. When it comes to consumption, you have an option to either have like a single consumer across a topic, which will consume from all partitions and will maintain its partition offsets for each of the partitions that you have. Now, as I mentioned, Kafka order is guaranteed at the partition level. So if you were to consume from multiple different partitions of a Kafka topic, your order would be guaranteed per each partition, but not necessarily across the entire topic. So if you do need a guaranteed order across an entire topic, then you would want to only have one single partition in order to maintain the ordering within the whole topic. There are also some other ways to do that, but we won't go too deep since this is a 101 session. As far as grouped consumers, you also can have your consumers run in a consumer group, and they will work together to consume from your topic. So in this case, if we have 4 consumers that are reading from a topic with 4 partitions, each of them will maintain its own partition, and therefore you can achieve high parallelism by having additional consumers to read from the same workload. Outside of standard hub sub messaging, which is really what Kafka started as, around like 0.6, it was your standard hub sub messaging type of model, which is really what we've talked about so far. But we also have the ability to do connections to external sources through something called Kafka Connect. It's a Java-based API for working with Kafka and then the external systems that you're consuming from and producing from and consuming to. So these are your typical data sources like databases, file systems, applications. There are a number of these pre-built connectors that have been built on top of the Connect ecosystem in order to connect to like industry leaders where most people are storing their data. Within the Connect ecosystem, sorry, one second. You have 2 options. So you either can have a distributed cluster of Connect workers, and that means that they would work together to consume from and produce to your external systems. So those Connect workers can be scaled out the same way that the Kafka cluster is. So it is highly scalable, and it allows for high availability because if you did have a Connect worker go down, then the tasks that were on that worker will be distributed to other Connect workers. Whereas a Connect standalone worker would connect to a single source of data and connect it to your Kafka cluster. But if you did have downtime because it's not working in a clustered fashion, that would just be downtime to the connection itself. So it can be okay in like development type of workloads, but it's not great for production because you don't have that high availability aspect. The next thing that was built after Kafka Connect was Kafka Streams. And so Kafka Streams is essentially a way of doing stream processing on the data that's sitting within your Kafka topics. It is, again, a Java-based API. It also can be used to build out like microservices, the T and ETL, right? So it's the transformational layer. And it allows you also to write continuous running queries and transformations on your data. So as the data is moving across the Kafka layer, you're actually running the stream processing right there within the middle layer itself. So you're not having to send it to an external system to process the data. Some examples of how this is used is for like monitoring your applications, looking at customer information. So a lot of people use this to, let's say you have a service that needs to be aggregated with some other stream of data that's coming from one of your databases or applications. You would use Kafka Streams for that. Fraud detection, sort of like we mentioned, right? So tracking certain number of changes over time that look fraudulent, whether that's clickstream data or payments data. Really the opportunities with stream processing are endless. This would be comparable, as I mentioned, to something like Storm or Spark Streaming or Flink or anything you might be familiar with. It's similar to Kafka partitioning in that you are spread out over multiple tasks. So instead of like Kafka Core, where a topic gets its parallelism by having multiple partitions, Kafka Streams gets its parallelism by having multiple tasks that process your data and then rejoin it, and they do output the results to a Kafka topic to then be consumed by downstream systems. So the difference between a stream and a table is that within a stream, you will have just every event that you've had, and so it'll store those records forever. Whereas you can have a table within Kafka Streams that is more like a materialized view, and it's continuously updating from the results of the stream. One of the newer advancements in Kafka is something called KSQL, or KSQL DB as it's now referred to. It's a little different than streams because it's kind of an abstraction layer away from Java processing so that you're now doing SQL-based processing. The example that I gave here is just what it would look like in Java code versus what it looks like in SQL code. So as you can see, it's just a lot less code to have to maintain. And the example that I've given is that you want to create like a fraudulent payments stream from a topic called payments where a variable called fraud probability is greater than 0.8. So as you can see, it allows you to do things like joining, aggregation, filtering, window functions. It's really like high-level stream processing use cases. So some example use cases for KSQL would be things like data mining or exploration. If you need to enrich your data between multiple different sources or write streaming ETL queries, you can filter your data, mask it as need be, and also do some amount of monitoring and anomaly detection as well. Sorry, I talk all day. You would think that I would have a voice here. But the final thing I wanted to touch on is who should manage your Kafka cluster. And I wanted to touch for a second on what it looks like in the cloud because this is a cloud meetup. You have sort of two major options. You can either self-manage your Kafka cluster or you can go with a fully managed solution. Specifically in the cloud, I would think that most of my customers lean toward fully managed offerings because they do have faster time to live. They don't require as much Kafka knowledge. So it's sort of like taking away the need for DevOps within Kafka and allowing you to just write code on top of it. they lower your burden from an operational standpoint, and they allow you to have SLAs around uptime that are influenced by other companies. So as opposed to you having to maintain your uptime, you have SLAs around knowing that it's going to be up for a certain amount of time. I would say the trade-off there is that you don't have operational control, really, so you are subject to the configurations that are placed upon you by your providers. Self-managed is like the complete opposite in that you do have that granular configuration control, so that can be really good for companies who know and understand Kafka, but you do have a higher DevOps burden because of that, and therefore you have to have internal resources who know how to manage and understand Kafka as well. Okay, so with that, that's my presentation for today. I did link a number of resources, so Paul, I can share this presentation with you if you want to share it with the group. That can get you started if you're interested in learning more about Kafka. But otherwise, I will take questions that have come up.
That's amazing. And that was one of the questions, Amanda. Thank you. The folks here did want to know if you would share the slides. So if you want to send them over, we can post them on the Women Who Code site. That would be amazing. And we will do that. There are a number of questions in the chat, so maybe I'll just go from the top down, and let's see, the slides will be shared. There was a slide early on, I think when you were talking about what I would think of as more existing or maybe even legacy environments, that there was an acronym MOM, and I wondered if that was Microsoft Operations Manager, if it was something else.
No, sorry, I should know that. Shouldn't have an acronym. But it's a messaging acronym, so like a messaging system.
Okay.
Hold on, let me see what exactly it stands for.
So is it something?
Message-oriented middleware.
Ah, okay.
Yeah.
Okay, got it. That's so funny. Operations Manager is an even older thing. So that was one question. So message-oriented middleware.
Exactly.
And for where I can find the webinar recording later, we do post these to the Women Who Code YouTube channel. If you do follow Women Who Code on Instagram or LinkedIn, the information will be posted there as well. And I will invite my Cloud Fellows to pipe in here. So yep, that was actually answered in the chat. There was a question about asking if we should think of Kafka as the software needed to create an event-driven architecture. So if you had to say, what is Kafka, how would you summarize it?
Yeah, when I think of Kafka, I really think of it as like PubSub Plus, right? So it's really more like a streaming middle layer for your systems. It's one of many technologies I would think that are needed to create like an event-driven architecture. And there are ways to do event-driven architecture without using Kafka. So there are other tools that people use to make event-driven systems, like Kinesis, for example, right? Kinesis is more of like a PubSub type of messaging platform. People use it to create event-driven architectures, but it has limitations in terms of how long you can store your data, and also how large your messages can be. So Kafka removes some of those limitations and allows for more possibilities in terms of which model you want to go with. Does that answer the question?
I think so, but if not, feel free to post back into the Q&A or the chat. And then there's an interesting question about partitions. Do the partitions replicate data, or is the partition only designed for sharing load across my brokers? And if a topic is not partitioned, is the topic placed on one broker?
Yes, so great question. There's many different levels to that answer, so I'll try to hit them all. The first piece of it is partitions the same as replication? Not necessarily. So within Kafka, you will have a number of partitions for your topic, and that's how the topic is split up and spread across brokers. When it comes to replication, you'll also have something called a replication factor. So let's say you have a replication factor of 3, then each of your partitions is replicated 3 times. So it will be replicated across various brokers too. That way, if you do have downtime on one of your brokers, then it will be replicated somewhere else. What was the third part of that question, Paula, just so I make sure I hit it?
If a topic is not partitioned, is the topic placed in one broker?
Exactly, yeah, that is the case.
Okay.
Unless you have a high replication factor. So if you do have like a replication factor of 3, but you only have one partition, then it will be replicated across multiple brokers. But it'll be the same data that's replicated.
And this ties into that set of questions from a real world example. Can you give examples of a topic, a partition, and a broker?
Sure. Yeah, that's a great question. So let's say like we have a customer topic that stores within its message, it has like the first name, last name, email address, phone number, right? Just some customer information. That would be your topic. Within your partitions, you might partition, let's say you partition based on first name or something, right? Then all of the Amy's would go on one partition. All of the Johns would go on one partition. Depending on the number of names that you have, let's say you had 100 different names and you had 3 partitions, then you can imagine that hopefully you would have a decently even skew across your various partitions. As far as brokers go, I would just think of that more as like the ability to scale up your processing capabilities. So if you have a single broker, it's going to come with its own set of CPU, storage, memory, right? So that you have a certain amount of storage power, processing power, and then as you require additional like throughput or additional storage or additional partitions which utilize CPU, then you would add additional brokers.
Awesome. And then there was another acronym question, and
Sure.
similar to MOM, what did ESB stand for?
That's like Enterprise Service Bus, I believe is what.
Yeah.
Yeah.
Yeah, and I guess that, yeah, depending on your implementation, those two things are very similar. It's about the flow of messages through a system.
And that really is kind of the point, right? Is that a lot of these different technologies, you have to have multiple different technologies because they all have their own slight different use case. Whereas Kafka can replace a number of these different types of technologies. Now that's not to say that it has to, right? If you have a system that a Tunity is the right fit, it's the perfect fit, and a Tunity is like a data movement tool, right? It's the perfect fit for doing some sort of brief ETL and moving your data from one source to the other. You don't have to tear it out and replace it with Kafka, you know what I mean? But it's more like if you have 5 different systems for moving data in slightly different ways, and then you have a stream processing system, and then you have, a connection system to bring in data from different places, it can clean up your infrastructure a bit to replace that with one tool that is a single streaming tool at the middle layer. And that's what I see a lot of my customers do, is they want to get rid of those point-to-point connections, and they want to get rid of the technical debt of maintaining 5 different systems to do similar things.
Yeah, and that's a sort of a segue into tooling. There's a question on the level of tooling available for teams wanting to build full event sourcing. For example, how easy is it to replay a state at a given time, and for things like DevOps use cases like blue-green deployments? So what level of tooling is available for teams wanting to do those kinds of things?
Yeah, Kafka is made for being able to replay data as long as it's stored on the event layer. So it is really made for event sourcing. I would say that the restriction comes more in the amount of storage that you have at the event layer, because as we've already mentioned, it's distributed, it's replicated, it requires a large amount of storage if you're going to store indefinitely. There is a pretty good amount of tooling built into Kafka to make this sort of thing like more possible. So either things like I mentioned, kind of compacted topics, there is tooling built recently around tiered storage. So one of the newer features within Confluent platform, which it is enterprise IP, so it's not built into the open source community yet, is actually using a secondary, cheaper data store. So something like S3 it's currently in preview, so it's only S3 for now, but it'll be like S3, GCS, HDFS, so cheaper storage systems, and separating out the storage from compute so that you can archive data over time, and only pulling in the data that you need at the time of processing. So I think that the tooling is getting there more and more for long-term retention and allowing event sourcing to be an option. But yeah, natively, that it is kind of what Kafka is built for. It's more of the difficulties around pricing at that type of level, if that makes sense.
That's, you're almost playing right into the flow of questions here, because the next one is, can you talk about the trade-offs of Kafka for more of a startup use case versus enterprise, for example, cost?
Yeah. I think that's an interesting question. I would have to know more about like the specific use case. So there are always trade-offs, right? And I think like if you're in a startup use case where you really just want to get started and you want to get your feet wet, there are other tools that work well for that, things like Google PubSub or Kinesis, and there's nothing necessarily wrong with that. It'll just be difficult at scale to maintain something like that. And a lot of these capabilities, if you look at like Azure Event Hubs, they come with their own set of problems in that they typically don't have the same integrations to like external systems that Kafka has built in with Connect, or they're lacking the really good stream processing layer that Kafka has. So it is more of an all-inclusive use case, and it works at small scale as well as it works at large scale. So it's not necessary that you have a large scale use case to get started with it. I don't know if that answered the question, but it just more comes into how you actually want to deploy it. So getting started with an ephemeral use case, either on a cloud-based thing like Confluent Cloud or MSK, is fairly simple, or spinning up your own single node cluster. And I can add in resources around like quick starts for Kafka when I send over my slides as well.
Yeah, I find it always fascinating because, one of the aspects of architecture is cost of change. So if you start small, or Google PubSub or Event Hub, what's the cost of change as you evolve? And those are always the good architectural questions.
Right. Well, it's difficult, right? Because you also, on the flip side, like you don't want to over provision for a Kafka use case. And this is where I think that the managed services and the cloud providers are really having a good play here. Because in order to spin up a Kafka cluster provisioned correctly, right, and able to handle a number of Kafka use cases, it's going to require Kafka knowledge on your internal teams, people that can maintain it, so a DevOps team or an internal team that just works with Kafka and takes on the DevOps responsibility. So when you do work with like a managed service provider, you have the ability to go in, just spin up a Kafka cluster on a managed service, and not have to worry so much about the DevOps, and be able to just try out those introductory use cases and allow it to grow with you as you add additional use cases.
Yeah, awesome. And there's a couple more here. One is streaming only recommended for close to real time? For example, fraud detection, ads, data needs. Might batch be easier to implement and maintain if that use case is not critical? Can you talk more about the maintenance level of effort between batch and stream?
Yeah, I mean, that's an incredible point, right? I like to make this joke that once we all started learning about big data and stream processing, that we all started like Marie Kondoing our architectures and throwing out all these things that were working fine for our use cases because we were like, oh, we don't need those anymore. We have all these new technologies. And I don't think that's also always necessarily the case. Sometimes there are batch systems and batch processing works just fine. Sometimes there is small data and you don't need to implement big data processing, right? There is complication that comes about when you're writing stream processing code. Obviously, it's a lot more code to maintain. It comes with its own unique set of difficulties. So I would say yes, typically this is more for real-time type of use cases or data movement use cases. So let's say I have two separate databases, like I have an underlying RDBMS, and I'm also trying to spin up some microservices architecture in the cloud. I need something in the middle to communicate as there are changes made to my underlying database. And I want that to be typically like closer to real time if I have anything that is using those applications within like the cloud layer. So I hope that makes sense, but it doesn't mean that you have to go this route if you don't have a stream processing type of use case, or you don't have any sort of bridge to new architecture. You definitely don't have to go down the Kafka route if batch processing is working for you.
And here's a little bit of a different topic. I am a complete beginner. I found today's presentation to be great. However, I was wondering if there's hands-on material to get started, even with even more basics, unless this is not possible since those concepts are embedded within an existent bigger structure. So how to get started if you're a newbie.
Yeah, I will definitely be sending over some like quick start type of guides for Kafka. And I also am sending over some of the like best Kafka books that are out there, which I think are great places to start so that you understand conceptually what the tool's used for as well.
Okay, and then thank you for your earlier answer on Kafka and EDA. Could we get a simplified bird's eye view of how to think of Kafka if one so far is only familiar with Spark Hadoop relational database and NoSQL? I am having trouble understanding how this fits together, and when do we say that we have a need for Kafka?
Sure, yeah, that makes sense. So if you are having a hard time keeping your various different data sources either in sync, or if you have a need to transport data between those various systems, that's typically where Kafka will come in. So the way I like to think of it is really as an asynchronous messaging system, meaning that it is a single layer in the middle between different systems that allows you to decouple your producers from your consumers, meaning that I can have multiple different producers writing to this single middle layer, and I can have multiple different consumers consuming from it. So instead of having to set up a connection from A to B, and then A to C, and then A to D, and so on and so forth, right? I can have this middle layer that stores the data, and I can have various services that connect to it to keep my data in sync between my different services. So maybe that's HDFS is one of your producing systems, and then you have a Java-based application that needs access to some amount of data that's stored in HDFS, and then you have a NoSQL database like Cassandra that has to have access to a certain amount of data that's sitting on HDFS, and you want to just be able to write that data from HDFS into one place to be then pulled from multiple different places. That's where Kafka would come in.
Awesome. And I've got a good question here. It sounds like Kafka could be a good solution to synchronize data across ERP systems like Dynamics AX, JD Edwards. Am I on the right track here? For example, item data that needs to be synchronized across multiple ERP systems.
Yeah, definitely on the right track. So if you have some sort of event that happens and then you need multiple different systems to consume that single event, that's where Kafka would come into play. There might also be some amount of transformations that happen on the Kafka layer that those downstream systems then read from. All of that can happen within this one middle layer. It's kind of like the single like source of truth between multiple different databases, multiple different applications, because as we added more and more applications, more and more databases, more data warehouses, different data stores in general, it became difficult for them to all communicate with each other and stay in sync. That's where the need for Kafka came about.
Yeah, and that's I've had some adventures in those kinds of environments, and typically one of the challenges is I've got this old legacy system And the challenge is, how do I get the information out of it? You know, how do I become a producer at an event level instead of just a batch level? And there's always some really good adventures in dealing with legacy systems and trying to turn them into real-time producers of information versus batch producers. So that's very cool. I do think, yep, I've gotten through all the questions. We have 5 minutes left, and I want to just be very grateful as well for the whole love Marie Kondoing architecture comment. I think that this is now becoming a meme. I've held so many architectures in my hands that did not give me joy, so thank you for that.
You're welcome. Yeah. Yeah, thanks for having me. This was a blast. So I'll make sure to send you the slides and you can share with whoever. And I look forward to hearing some of you guys present in the future as well.
Yes, please. If you are on the call here and you have a topic or an adventure you'd like to share with Women Who Code, please hit us up and tell your story. We want to hear your voice. And thank you once again. Thank you so much, Amanda. This was a great session, and we'll share it all out.
All right. Thanks.
Thanks, everyone.
Bye.